We're going to start talking about our unit on circles, first by talking about lines and segments that intersect circles. So there's a couple that we are already familiar with, radius and diameter, which go through the center, or start at the center. We're going to expand on that and look at some other types of segments and lines. So the first is a chord. So a chord, like you see here, is a segment whose endpoints lie on a circle. For example, this chord AB. Alright, the chord can be a diameter if it goes through the center. So a diameter is a special chord. However, not all chords go through the center. Okay, so again, just to be specific, a diameter is always a chord, but not all chords are diameters. So the next one we have is a secant. So a secant is basically, instead of just being a segment, it's going to be a line that intersects a circle. And again, it doesn't have to go through the center, but it will contain a chord. So the secant here is line L. Alright, and finally, one that's important is the tangent. Not to be confused by the trig function tangent, but when we're talking about a tangent to a circle, it's a line or segment that intersects the circle at exactly one point. So it's going to hit exactly at one point, and that point is called the point of tangency. Alright? So those are three other types of lines or segments that intersect our circles to go along with radius and diameter that we're already familiar with. So we can also talk about other vocabulary here: congruent circles, concentric circles, and tangent circles. So congruent circles, pretty important if we're given congruent circles. We know they're congruent if they have congruent radii, because remember, that's the only measurement, right? That was really important, the only unique measurement in our circle. So if the radii are congruent, then our circles are congruent. So this notation here, the circle with the dot in the middle, this just says, circle. And you name the circle by its center, right? Circle A, circle B, etc. Concentric circles are circles that share a center. Not as important with what we're doing here in this unit, but kind of nice to know. Tangent circles might come in handy when we see them in a diagram. So they intersect at exactly one point, and that point would be the point of tangency. And for example, if you look at these externally tangent circles, you can find the distance between the centers by just adding the two radii, right? So again, just kind of interesting things to consider. Right, so they intersect at a point of tangency, they only intersect once. Okay? So we have some theorems we're going to deal with, and drumroll, with theorems we are also going to come back to some proofs. So, kind of coming full circle here at the end of our course. So the first theorem deals with this picture here. So you're going to be given a tangent, a line that or segment that is tangent to a circle. And what do we know about this? So if a line or a line segment is tangent to a circle, then it is perpendicular to the radius or diameter that intersects that point of tangency. So if we're given that L is tangent to circle A, then we can conclude that AB, that radius, is perpendicular to L. So it's going to create a 90-degree angle at this point of tangency. Okay, and the converse of that would also be true, and that's our next theorem. So this says if a line or segment is perpendicular to a radius or diameter at a point on a circle, then the line is tangent to the circle. So again, it's the converse. So we're told that this line M is perpendicular to CD, right, at that point D, and we can see CD is a radius. And you can extend that to make that a diameter, it doesn't matter. Then what we can say then is that M is tangent to circle C, right? Because it creates that 90-degree angle at that point D, that single point D. Okay? Finally, our last theorem of the day here. What happens if we have two tangents coming from the same external point? Well, here, again, if we have two segments that are tangent, right, to a circle, and they both come from the same external point, so they both have the same starting point here at A, then those segments are congruent. So if we're given that AB and AC are tangent to circle P, and you can see how they have the same start point A, then we can conclude that AB is congruent to AC. And this creates a kite. If we connect P to B and P to C, we have two pairs of corresponding sides that make a kite. Just interesting fact there. Okay? So those are our three theorems we're going to be using today. We've got a couple examples. So one, we can work out some values, and two, a proof that we want to get back into thinking about. All right? So typically with problems like example 1, it should tell you that the lines are tangent. If not, you can always ask me, but typically we will assume that they are tangent. So HK and HG are tangent to circle F. What's the value of HG? So remember, this notation means find the length of HG, right? So that's what I mean. Don't just tell me HG is, 4 plus 2a, but see if you can find that value. So what do we know about this? Well, we know that we have two tangents, right? HK and HG are tangent to circle F. So what does that tell me? Well, based on that last theorem, that tells me that HK is congruent to HG, right? And then by our definition of congruence, we know that HK is equal to HG, and then I can substitute to solve. So, back to solving some equations, right? And then we can solve that for A, and then plug that in to find HG. And there we go. So that is all done. HG should be 28. Hopefully you got the same thing. Okay, so not a really complicated problem, but once again, think about what if we had quadratics, right? What if it was 5a squared minus 32 equals 4 plus 2a? Things like that. And remember, not everything's drawn to scale, so if you look at this, I might say, wait, look, HK looks like it's going to actually be a secant. Don't worry about it. Go with the tangent. Again, typically, if you see a drawing drawn like example 1, it will be tangent. If you're not sure, just ask me to see if you can assume so. But typically, we will assume that drawings like that are tangent. Okay? Finally, let's wrap up with a proof. All right, two-column proof. Given that AB and AC are tangent to circle P, prove that AB is congruent to AC. So we are proving this proof. Before we jump into this, one thing I want to remind you, we did have other theorems. So in your assignment to go with this section, make sure you reference that, the 90 degrees and stuff. So that is important. So if we had, problems where you're solving for the angle here at CD, let's say K or whatever, that's 90. So just, again, keep that in mind. We don't have time to do examples for everything, but we want to make sure we know those theorems. Okay, but anyway, back to this proof. We're going to prove that third theorem. How do we know that AB is congruent to AC? Well, remember, you might look at this and be like, I don't know, it just is. But you can always draw in auxiliary lines. And remember, what shapes are we very, very used to working with? Triangles. Hopefully that's what you said. So what I can do is I can draw in a couple radii, because I know radii are measurements in a circle, and then I can draw in this extra PA, right? And why do you think that would be useful? Because PA is reflexive. So hopefully you guys are thinking CP-CTC, congruent triangles, right? So here's my plan. I drew in my radii, and what do you always know about radii? Well, all radii are congruent, right? Right? And then lastly, what do you know about tangents to a circle? Well, remember, they create 90-degree angles. So I've got hypotenuse leg, right? So this is reflexive, and that's your hypotenuse because it's across from the right angle. And then I can use CP-CTC. So you can always go back to looking for those familiar shapes that we are very, very used to working with. So here's my proof. So I just started by stating what I drew in. So I specifically drew in radii because any segment, if that's not clear, that's abbreviation for segment, from the center of a circle to the circumference is a radius. And then I can draw in PA because any 2 points create a segment. So you can connect any 2 points to create a segment to work within your proof. And then I was given my tangents. And remember, what I'm looking for is I'm trying to get to CPCTC, so I want to show that the triangles are congruent. And what I said earlier was, look, right triangles, so let's try making HL work. So I'm going to go ahead and state that since I have tangents, I know I have right angles. So because I have those tangent lines, I know they're perpendicular to the radii, which I specified above, right? So 1 links me to 4 because I have radii. And there's no name for that theorem, so just abbreviate it, right? Tangent lines perpendicular to radii of a circle, just get the gist of it. And then I have those right angles, which are great because hypotenuse leg only works for right triangles, right? And then we can keep going and say how I know the legs are congruent because they're radii, and PA, the hypotenuse, by the reflexive property. And once I have that, we've got the right triangle, the right angles, congruent legs, congruent hypotenuses, then we have HL. And that HL leads me to CPCTC. All right? So be prepared to prove, right, anything using our new theorems. We're going to be doing proofs throughout this unit. And let me know if you have questions. Thank you for listening.